Boys from a school in South London improve their 3D awareness by looking at buildings, making paper shapes, and exploring the algebra of origami. Students from Woolwich Polytechnic School for Boys are looking at the Greater London Authority's City Hall. It's part of a project to improve their 3D awareness. So here, they're looking at the shape and structure of buildings.
What's so special about City Hall?
I see a lopsided sphere pushed onto one side.
I think because it's like a curved shape, the wind won't hit it like face on like maybe some of these buildings, so it might be structurally more sound.
The reason it's got such a curved edge is to kind of avoid as much surface area from being hit from the sun.
Well, on the building there's like the layers on them, and I think it might be for shading, like if the sun was above.
They move on to look at the iconic Gherkin building in the City of London.
This is very good. We have equilateral triangles. Also, they form diamonds as well. So
none of it's curved glass, except there's only one piece of curved glass, and that's at the top. All the rest, it's like almost an optical illusion. It's all just flat, normal glass.
Each triangle feeds onto the triangle below it in the glass and the structure.
If air can flow very, nicely.
Back at school, there's a tutorial about the trip with their maths teacher to challenge these higher attaining Year 9 students.
What were the important points that we've discovered and discussed during that trip?
each building was constructed by various shapes, and the shapes seemed to tessellate. So that was a big thing we would notice.
What's the impact of the tessellation, the fact of using the same shape over and over and over again?
You wouldn't have to manufacture an individual piece, in which case you'd have to manufacture an individual mould for each piece.
So that was one big thing. The tessellation of the shape allowed us to be very cost effective, and also because those shapes are not that big, they didn't use the diamond, they used the triangle.
So when you make a skeleton around it full of triangles, which is supposed to be the strongest simple shape, obviously you're making a very strong shape.
What were the other important facts that we've seen about the Gherkin?
You can't see the top, or was it you could see the top? So
Yeah.
It's a bit you don't feel like it dwarfs you.
Right, and the fact that with the angle you wouldn't see the top of the building, so exactly like you said, it wouldn't dwarf.
Less because it bulges. One floor will have more triangles than the one below.
So how do you do that then?
Well, you could change them in size.
Yeah,
technically,
but then your tessellation is lost, and your cost effectiveness is lost, isn't it?
Yes, but if you could change, you could only create one mould for each layer, though, because if you just continue with it.
36 times one mould is not that cost efficient, is it?
Yeah.
No.
We're going off the point. I don't know what I'm saying. You should have a member of Year 9 on your...
In the next part of the project, the Year 9s lead a Year 8 session on the properties of 3D shapes.
How many edges are on a triangular prism? 9. Vertices. How many vertices does it have?
8. 6.
1, 2, 3, 4, 5.
The purpose of the exercise today is to create an enjoyment in mathematics, increase the 3D awareness, because a lot of boys don't have much 3D awareness and they're not really clear about edges, vertices, faces.
Edges, I think 4. 1, 2, 3.
That's a triangular prism.
You got 1, 2,
1, 2, 3, 4, 5, 6. How many edges? 1,
5, 5,
3, 4.
15, 3, 4, 8. 8 to 2. 10. Yeah, 10.
1, 2.
I believe that in our syllabus, sadly, we don't have that much space for 3D work. So it's very important to make sure they can imagine in their head, and that's a process that they need for any 3D work, really. We've got 8 faces, not 8 vertices.
15 10 by 10 is 5 plus 2 is 7.
Some students begin to work out the connection between faces, vertices and edges.
Did anyone have time to find out the patterns between the faces, the vertices, and the edges? Yes, let's take them.
If you take the edges, if you take the vertices and take them away from the edges and then add 2, you'll get the amount of faces.
That is correct. Well done, guys.
Okay, we're going to make one of these, a dodecahedron. Now, this is all held together by itself. There's no gluing or tape involved in this. So the first thing you want to do is fold your piece.
Part of the paper folding exercise is obviously to obtain a dodecahedron,
straight down the center.
but it's also for the boys to do something kinesthetic, because that's something that we need to, I think in mathematics right now, a lot of mathematics is sometimes seen as textbooks, exercises, and they don't do things.
You're going to take this corner, you're going to fold it down, just like that.
For a lot of boys, the kinesthetic aspects is very, very important, whether you do locus outside or you do paper folding.
So each table has to make 30 of these. And I just want you to remember that accuracy is key, otherwise it won't look like this, it will look like, well, not like this.
How the hell? Stick them together, yeah.
Take this, line them up,
Push. This isn't even accurate.
push it in there. Oh, that's it.
This is cool.
So we have this part. We lift up one of the sides, one of the folds, right?
We had year 9s taken out of their lessons to, in fact, teach the year 8s.
Keep going, you've got to push it all the way through. And then what should happen is it should lock. So you just like hold it like that and it shouldn't fall out. Okay.
It builds their confidence really tremendously, and their mass understanding sinks in.
Try it from that side, it might be a bit easier. It does help you learn if you teach others, because if you teach others, it means you already have that knowledge, and it's just every time you teach others, it's kind of enforce that knowledge that you have and things like that.
Well, it's a new thing. I mean, in school, the teachers do try to get us as involved as possible, but teaching is, it's a new thing.
And then you do that.
For the other boys, it really creates a good relationship, because they see boys who are, in their school, who've been through the same syllabus with the same teacher, who are able to grasp that concept.
Now the very important thing is that every single kind of like circle that you do, there will be a pentagon. And you're going to make another little pentagon here, and another little pentagon here, and another little pentagon here.
Start connecting that to this. This one's really bad.
Who's asking you?
This.
I threw that one into the hand like...
I need to connect it.
I know, but it's going to be easier if you're going to...
I'm holding it. Who's going to do
There's
it?
the last piece. There's the last piece. There's the last piece. I'm holding the last piece. Woo!
Good for you, Jacob.
No,
No, that would not slot in there. That will slot there. I want to do it.
We're not finished. Well, this part of the project is supposed to be about geometry and, mainly just having a fun reprieve and still learning at the same time. That's one of the important things, to try and get away from so much the textbook and look at more unorthodox, means of teaching. That's the main objective, and I think we've achieved that rather well. It can be frustrating as a teacher, but I do it for the kids.
Finished! Yes! That looks a bit...
What we're going to do today is a folding paper exercise.
As part of the paper folding theme, maths teacher Alwyn McCollin is trying an activity about the intersection of two paper folds with his year 11s.
The next thing I want you to do is to make a fold from right to bottom left.
There was a lesson that involved finding the perfect thirds and how to prove it, whether geometrically or using straight line equations. So again, linking practical activities to more theoretical, if you want, math.
What I need you to do is for you to tell me, if you take this square, how much of that square is that fold that you have, that you've done, that you've made?
1/3.
But how can we prove that's a third?
Work out the equations of the lines.
Work out the equations. Brilliant. Now, how are we going to work out the equations of straight lines?
That's one square, so that's counting as one square. So the gradient of that line will be, that would be 1, because every 1 you go across, it goes up 1.
Brilliant.
And then this one will be half. Well, no.
It would be y equals x.
That will be.
That middle one.
Yeah, that one will be y. That one will be gradient of -1.
Yeah.
Why is it a gradient of -1? It's very interesting because a lot of the stuff that's done within that practical exercise is not about isolating each topic area, but bringing all topic areas together and using them as a means to an end. They're not sitting there thinking, okay, today I'm doing one particular topic. They're using a range of different topics in one session. It's like getting them to appreciate, today I'm not doing maths, but I'm doing this particular exercise. It's almost like if you have a carpenter using measuring something. He's not thinking, well, today I'm doing measurement. He's just using it to do his particular job. And the idea is to get him to understand that maths is a tool that we can use, and it's not some abstract thing that we just use in the classroom. I want you to discuss it and then write out the equations of both straight lines.
Write down the equation
I'll give
of
you
straight lines. So this one's y equals...
5 minutes. 5 minutes to do that.
Is that... And the other one's y equals 2x.
Which one?
This one here.
Oh yeah, mine.
That one's that, and then that one's that.
They interacted more with each other, discussed more things with each other, and they thought more about what they were doing.
So it will be the origin.
That's the origin.
0, 0.
0, 0. And then this line intercepts at the y-axis here. So this would be the y-axis, and that would be the x-axis. And this line down the middle intercepts at 1. So you put the +1 at the end of the thing.
So, by thinking about the equations of the folds, they begin to prove that they intersect a third of the way across the paper.
These two lines intercept at, they intercept at 0.66, 0.33, don't they?
What's the x-coordinate?
X-coordinate is 0.33, and the other one is 0.66. Y-coordinate is 0.66.
They're working together to solve problems, because that's what actually happens in reality. A lot of the problems aren't solved in isolation, they're solved together. Compare this.
They move on to think about some generalizations.
If I want to fold it into fifths.
If you wanted to find a fifth, fifth, you'd fold it 4 times, then add 1 would give you the fifth. But really, it should be the number minus 1 is what you fold, and then because of the gradient, you're adding.
Right, so can you put that down then?
1 minus x equals n plus minus 1 in brackets x. So if you just change the n to the number you want to find, then x will be the... Yeah. No, basically, no, x will be how much you have to go across to go up to this thing.
Number of folds.
Easy. That's so good.
At the beginning, they would have never thought that folding paper had anything to do with maths. But by the end, that connection is made.
So what was the philosophy behind the whole project that involved visiting local buildings, discussing their design, making paper dodecahedrons, using students as mentors, and exploring the algebra of origami?
We're realizing that instead of teaching them facts and how to apply them, what we need to understand is we need to make them understand. It's not about memorizing facts. It's about them having an understanding of maths. And if they've got an understanding of maths, then they will be able to, see that number is used in everything. That you can use algebra to do shape and so forth. So if they get a proper understanding, then at the end of the day, they will be much better mathematicians.